Hi students, in this video we are going to discuss about the realization of FIR filter. So using the design techniques we have designed the transfer function of the filter. Now using this transfer function, if you want this is transfer function is nothing but the here you are having an FIR filter, you will have an impulse response h of n. In Z domain you will represent the transfer function. When you give an input x of n, you will obtain an output y of n. Okay, so here this x of n will be represented in Z domain as x of z, and this is represented as y of z. Okay, now here in the using the design techniques, what we find out the transfer function of the filter. Okay, so what are all the things in the transfer function you will have? So in the, for example, if you have considered any design techniques, the result will be like this: h of z plus 2z inverse plus 3z power minus 2, like that you will get the output, right? So here what is the meaning of this? This is the responses. This is the coefficient of the transfer function. Okay, so here what we are going to do is h of z is equal to summation n is equal to 0 to n minus 1 h of n z power minus n. So by expanding this you will get h of 0 plus h of 1 z inverse plus h of 2 z power minus 2, like this. Okay, and also you know that h of z is equal to y of z by x of z, and this output can be written as h of z into x of z. Okay, so comparing these two things, otherwise you can write the values of h of z here, so you will get this equation. Okay, now when you multiply with this equation you will get these things. Okay, now see, if you want to realize this transfer function, okay, so realize, if you want to obtain this output, what you need what all the operation you need to perform here is you need to multiply your input with your h of impulse response. So for this you need a multiplier here. In order to perform this addition you need an adder, and also you require a delay element. You, in the first class itself we have derived one relation, right? We have discussed one relation, that is summation k equal to 0 to m minus 1 bk x of n minus k, right? So here this bk is nothing but this impulse responses. Okay, so when you substitute k equal to 0 you will get b0. b0 is nothing but h of 0. When you substitute k equal to 1 you will get b1. The b1 is nothing but this h of n. So this represent the coefficient of the filter. Now this represent the input. This input is here. When you substitute k equal to 0, what you will get? You will get x of n. When you substitute k equal to 1, you will get x of n minus 1. This represent the present, this represent the delay. So here when you take the z transform for x of n, what you will get? You will get x of z. When you take z transform for this, you will get x of z into z power minus 1. So here you need, in order to realize this x of n minus 1, so here what you need a delay element. So in order to implement x of n minus 2, so how will you perform this in z domain? X of z into z power minus 2. So what you need a 2 delay. Okay, so the same manner here, if we take inverse y of n, you will get x of n instead of h of 0. So what you will get is h of same thing, h of 0, which is nothing but here b0, plus h of 1, you will get h of 1. Then here you will have z inverse into x of z. Now z inverse, so z inverse into x of z is nothing but x of n minus 1. So you will get x of n minus 1. So plus, and the next term you will get h of 1 into z power minus 2 into x of z. So for that what you will get? You will get h of 2 x of n minus 2. Similarly this will extend up to h of n minus 1 x of n minus 1 delay. Up to this delay element you will get this. Okay, so here in order to implement this transfer function, what are all the things you need is you need an adder. Okay, so you need a multiplier and you need a delay element. Okay, so using these three elements we are going to realize the transfer function of an FIR filter. Okay, So a realization structure, here we can realize in three form. One is direct form or transversal structure, cascade realization and linear phase realization. Okay, now consider this is the input. Either you can represent x of n or x of z. Okay, now I am going to represent this equation. So what I will get is here x of z, otherwise x of n. This is x of n, so it is multiplied with h of 0. So here x of n is coming in this way, so it is multiplying with an h of 0. Either you represent an arrow or this symbol in order to represent this. Okay, this one, this triangle symbol like this. Okay, so here normally you will use an indication. This indicates the coefficient h of 0. So when the signal comes here, so what you will get at this point, it will get x of n into h of 0. Next here the x of n is also passes through this way. So here when x of n is passes through a delay, what will be the output of the delay? You will get x of n minus 1. Okay, so this x of n minus 1 come in this way and it is multiplied with h of n. So you will get x of n minus 1 into h of 1. Okay, so you will get at this point x of n minus 1 into h of n. So this x of n minus 1 pass through another delay. So what you will get? You will get x of n minus 2. So this x of n minus 2 is multiplied by n h of 2. So at this point you will get h of 2 into x of n minus 2. Okay, similarly you will get, so here the delay element is x of n minus n minus 1. Okay, n minus 1. So this is multiplied by h of n minus 1. Okay, so finally you will get all the output. So you will get this function. Okay, so this is what the direct form realization. So in order to implement this direct form realization, it require n multiplier, that is n minus 1 adder and n minus 1 delay element. So these are all the requirement in order to implement a direct form structure. Next is a cascade realization. It is very similar to that of a direct form, but here what we are going to do is we are going to factor the given transfer function into some factorized form, some subfactors. Okay, you are going to have it in the form of factorized form. Then we are going to realize these transfer functions separately. Okay, so now this is what the structure. Now if I explain, you won't understand. I will explain this using the problem, then you will get understand the concepts of this cascade realization. Now we will see the problem here. Here see, here obtain the direct form and cascade form realization of the transfer function. H of z is equal to 1 minus 1 by 4 z inverse plus 3 by 8 z power minus 2 here. Like this they have given in two factor form. Okay. Now in order to implement the direct form, what is the first condition is you have to get single transfer function. Okay, so what we need to do is just multiply with this, multiply these two factored function, and you will get an signal, that is the transfer function like this. Okay, so now I am going to implement this. The input is x of n. So how we need to draw the structure is, first consider how many delays are there. Here I am having z power minus 4. 4 delay elements are there. So I have drawn 4 delay elements here. Okay, next here this is what your input will come. Here the first coefficient is 1. So the next coefficient is minus 3 by 8. Here the another coefficient is minus 3 by 32. Here the next coefficient is 5 by 64. Now the next coefficient is minus 3 by 16. Okay, now what we need to do, we need to perform an addition operation, right? So I am going to perform an adder operation here. So adder, here also an adder. So finally this is what your y of n. So like this you need to realize. Okay, so what you need to do, first you need to consider how many delay elements are required. Okay, so you need to write the number of, draw the number of delay element. Then first coefficient, here it is 1. Then the signal will pass through 1 delay and it is multiplied by minus 3 by 8. So here you should not use a subtractor. Here you are going to use minus 3 by 8. we are going to multiply the minus sign. Okay, then in this delay will this x of n will go through another delay, so it get 2 times delayed output, so it is multiplied by minus 3 by 32. Similarly 3 time delay, this is multiplied by 5 by 64. Here 4 time delay, it is multiplied by minus 3 by 16. So the like that you need to draw the direct form realization structure of an FIR filter. So in this cascade realization, what we need to do is we need to consider these two factors. Okay, so first we need to realize it. So here what I am going to do is I am going to realize in some different manner. Here I am going to consider the input x of n. Here I am going to write the delay in this order. Okay, so here how many delays are there? Here I am having 2 delay. I have drawn the 2 delay. Okay, now the signal is multiplied by 1 first, then it is multiplied by minus 1 by 4. Okay, then it is multiplied by 3 by 8. Okay, now it is going to add using an adder. So here also it is going to add using an adder. Okay, see here the same concept. Here in this manner I have realized this delay. Now here in this manner I have realized this delay, because here we are going to connect the cascade, that is output of the first is fed as an input to the another one. So here I have realized this separately, then I am going to realize this. Okay, in order to realize this similar manner, considered it here for how many delay elements are required? 2 delay elements are required, so you draw 2 delay elements. Okay, so here the output of this is fed as an input to this. Okay, so now here it is first coefficient is 1. So here the second coefficient is 1 by 8 and the third coefficient is minus 1 by 2. It is going to add using an adder. Here also there is one adder. So okay. So this is what your final output. Okay, now whether you understand the difference between the direct form realization and cascade realization. So here if the given is in the single form, you need to factor as these two as possible factors, then each factors are going we are going to realize separately. Now we will see some few examples in this. So in order to implement this for a direct form realization, so what we need to do is we need to first draw the number of delay elements. So here the total delay elements are 5. So I am drawing the 5 delay elements here. Okay, so 4, and here I am drawing the 5 delay elements. So here the first coefficient is 1, the second coefficient is 3, and the third coefficient is 4. Here it is 4, here it is 3, and here it is 1. Okay, so this is what your input x of n, or you can represent here x of z. Now it is you're going to use an adder. Here we are going to use an adder to add these preceding outputs. Here we are going to use an adder. Here also we are going to use an adder, and finally here it is your y of n or y of z. Okay, now this is what the direct form realization. Now here in order to perform this cascade realization, what you need is you need to factor this, then only you need to realize like in this format. First we will perform the factorization method. So here first you write down the coefficient 1 3 4 4 3 1. Now I am going to perform the factor. Here I am going to use minus 1. So 1 minus 1, so it is 2, then minus 2 2, then minus 2 2, so here minus 2 1, so minus 1 0. Okay, so here now the factor is 1 plus z inverse 1 plus 2 z inverse plus 2 z power minus 2 plus 2 z power minus 3 plus z power minus 4. If you can also factor this. Okay, so you can perform again factorization in this format. So 1 2 2 2 1. Okay, so for this what I am going to do is I am again going to use minus 1. So here it is 1. So 1 into 1 minus 1. So here 1 minus 1, result is 1, so minus 1, the result is 1, so minus 1, it is 0. Again I have factored here as 1 plus z inverse, and the resultant is 1 plus z inverse plus z power minus 2 plus z power minus 3. So now I am going to realize this structure. Now this is what the factored form. Now consider the first one. So here how many delay element is required? Only one delay element is required. So what is the coefficient? It is plus 1. So here it is 1. So I am going to add using a adder. So this is what the for the first one, the output of this is fed to one another that is structure realization structure. Here also the element is z inverse, one element, so the coefficient is 1. Here this one I am going to represent here. So I am going to add using an adder. Finally the output I got here. Now how many delay elements you required? You required 3 delay elements. So z inverse, so z inverse and z inverse. So what is the coefficient of this first delay element? It is 1. Second delay element is also 1. Third delay element is also 1. And by using an adder, here I am going to add using an adder. Then here I am going to realize this one. So here also there is an adder required. So the output of this is fed to this. So finally I have obtained y of n or y of z, and so this is what your x of n. So in this manner you need to perform this cascade realization. Now I will give two more problems. You realize and realize the structure, you realize the cascade realization as well as the parallel, that is direct form realization. So you try these two problems by yourself in both direct form and cascade realization. We will discuss the result in the next class. Thank you. In the next class in the next video we will discuss about the linear phase realization. Thank you.